Hello everyone, welcome to my channel. Today I'm going to be working on problem number 1602, find nearest right node in binary tree. Now this is a problem that I have never worked on in the past. As you guys know, most of the problems that I work on this channel are done for the first time, so that way I can go through the actual interview process and replicate the problem solving aspect of the question. So the problem states, given the root of a binary tree and a node u in the tree, return the nearest node on the same level that is to the right of u. So u is 4, which is value 4. So we want to return on the same level that is to the right of u, or return null if u is the rightmost node in its level. So the value that we're looking for to the next to right one is 4. So we're going to return 5 because on that same level we have 5. The next question is 2. There is no right value, so what we're returning is null. So it seems that we're actually returning the references. There are no nodes to the right of 2. Okay. This problem probably would have been just a little bit easier, but rather than returning the value, we're just returning the reference to the next node. The number of nodes in the tree is in the range 1 to the 10 to the power of 5. 1 is less than node.val, which is less than 10 to the power of 5. All values in the tree are distinct. U is the node in the binary tree, rooted as root. U is the node in the binary tree, rooted as root. Okay. So what we're looking for is U. What if we go through a node that does not have U in it? So let's say we return null here, and the tree node U is 4, but let's say we remove 4, and then let's see what it returns. Okay, so overall we can always assume that U will always be present, so that is not an edge case that we need to worry about. So the algorithm is actually, I am sorry, this algorithm should be after going through the edge case. Okay, so let's think of, we already covered all the edge cases. I don't think there is any other edge cases. The least value is 1, or the smallest value is 1, and the greatest value is 10 to the power of 5. We know that all the values are distinct, so I don't believe there are any edge cases. The algorithm for this is, let's see. So we need to do some sort of a level order traversal. So level order traversal is done through BFS, and the moment we find U, the root node with the value U, what we need to do is return the next reference node to it. So in the level order traversal, you'll automatically have it set that way, because you would be going from left to right. So there are two ways of doing level order. One is doing it recursively, and one is the most common way is using a queue data structure. So what we can do is we can do either one. Let me think about queue. So we add it to the queue, then we iterate through all of them, and the moment we find U, we just return the next reference. But I think just for the challenge of it, we're going to use DFS and add the nodes to a hash map with their corresponding level. So for example, level 0 will have 1, level 1 will have 2, 3, level 3 will have 4, 5, and 6 in that order. And to maintain the level, we can just use a tree map to ensure the level is sorted, and then loop through the map and return the next reference node in the list. So the map is going to contain a level and the list of values in that level. And then in the end, when we can just do like we loop through every single key, loop through the key set, and then once we find U, we return the next reference. So it's a pretty straightforward solution. Let's get started. So let's first create a tree map. Integer, and then this will be a list of integer map equals new tree map. Then we need to perform DFS. We pass in root, we pass in U, and then we pass in the map. Okay, then we create a void method for this DFS where we pass in the tree node root, tree node U, and actually we don't need U because we are not searching for U right now. And then we just need the tree map. In the tree map, what we do is if root equals null, so we do our edge cases, return. Otherwise, we add, so we check if map dot contains key root. Then what we do is map dot get root dot add root dot val. Otherwise, what we do is also we need level, which is 0 into level, right? So in here we just do level plus plus. So if map dot contains key level, map dot get level dot add. So map is going to get level, and then we're going to add root dot val, whatever it is. Otherwise, you just do map dot put level, and in here we put a new array list. Map dot get level. Dot add. We could do it like this, root dot val, or we could just do new array list and then list dot add whatever that value was, and then we just do level plus plus. Then we just call the DFS function. We put in root dot val. Sorry, we put in root. And also this is not going to be root dot val, it's going to be the root. So it's going to be integer, but then it's going to be the reference to tree node. So list map dot get level dot add root map dot get. Okay. If map dot contains key level, map dot get level dot add, then we increment the level. Map dot put level map dot get level. dot add root dot level plus plus. So we do root dot left level, and then map, and then another DFS, and here we do root dot right. This part is very important because you want to add the left and then right. In the end, so we have the level add, okay. Then what we do is we traverse through the tree set, tree map. So for map.tree set, and I map.keyset, if map.get I equals new. Actually, instead of doing equals, we just do dot equals, we do dot equals u. Map.get I dot equals u. Sorry. Map.get I, so we need to list the reference list list equals map.get I, and then for int x list, and it's not int x, it's x list, and then in here, if x dot equals if x dot equals u, so if u is 4, so we need the next value. If x dot equals u, so x is the actual value. So actually a better increment of this would be int I 0, x is less than list dot size x plus plus. If list dot get x dot equals u, if list dot get x plus 1 does not equal null, then we return list dot get x plus 1. Otherwise, return list dot get x. Okay, so let's just make sure we have it right. So we loop through the map. We get the list from the key set. So the first little list and the second list will contain 2 and 3. But let's talk about here. It's going to contain 4, 5, and 6. If list.get x plus 1 does not equal null, return list.get x. So if it is null, so So return the nearest node to the same level, that is to the right of you, or no, return null if u is the rightmost node. So if x plus 1 is not null, then we just return x. So let's see if this works. What are we missing on line 31? Line 31, expected. I have it. List tree map integer list tree node. Map, oh, equals new tree map. Let's see. Line 47. Keep forgetting these semicolons like it's Python. Let's take a look at the other edge cases. X does not equal null. Let's try that. If list I get X does not equal null. Okay, let's try. So, if list I get X does not equal null, try the, what is going on? Array index out of bounds exception, index 1. Map.get is x is less than list.size equals u if list.get x does not equal null. X plus 1. Oh, it's an index out of bounds exception. For some reason, I keep thinking null pointer exception. Okay, for this, we just need to make sure is less than list.size. So let's say we are here. Does not equal null. If x is less than list.size, and so if list.getX does not equal null, so let's say if it is null, then in the end we could just return null. Otherwise, if list.getX, if x is less than list.size, which means let's say the size is 1, then we just return this list.getX. Yeah, so this one now should work. If x is less than list.size, minus 1. So in this case, return list.get. Oh, it's never x, it's return null. Let's try it now. Let's try to submit this. Perfect. Sorry about the few hiccups in the middle. Forgot this condition right here where we're going out of bounds. Thanks again for watching. Let me know if there's ways you think I could have improved. Bye.